Alright, so in the previous video we saw that every positive integer can be expressed uniquely in the base b place value notation, where b is any positive integer greater than 1. This will help us in devising the two divisibility tests which are the focus of this section. So today we are going to see those tests. But before that we need this theorem. What this theorem says, we have a polynomial function p of x, which of course is going to look like this, where m is a non-negative integer and it's a polynomial function with integral coefficients ck. These coefficients ck are all integers. Now if a and b are two integers that are congruent to each other modulo n, then P of A is congruent to P of B mod n. Note one thing, that since P has integral coefficients, so if you evaluate P at an integer A, the result, the value of the function is also going to be an integer. So it makes sense to say that the integer PA is congruent to the integer P of B mod n. It's extremely straightforward, but nevertheless, let's see the proof. The proof is simply several applications of the parts of that theorem, theorem 4.2, where we saw the basic properties of congruences. And specifically this, part F of that theorem. Since A is congruent to B mod n, it follows from part F of theorem 4.2 that a to the power k is congruent to b to the power k mod n for all of these values of k. Okay. And then you can multiply both sides of this congruence by ck. That also follows from one of the parts. Hence, for all these above k's, we have ck times a to the power k is congruent to ck times b to the power k modulo n. Now you just add these congruences, all of them. That also follows, that will give you a congruence mod n. That also follows from one of the parts of theorem 4.2. Everything, just like here we have mentioned part F, the other uses of the other parts of the theorem have not been mentioned explicitly, but it's understood which parts we are using at which step. Adding all these congruences, we get, let me write on that side, if I use summation notation, then it will look like this. Summation k goes from 0 to m, ck a to the power k is congruent to this mod n. It looks a little odd that I have written mod n here, but I have run out of space. So if you run out of space like this, it's better to actually write the congruence symbol here in the next line and then continue. But you understand what it means. That is, this is nothing but P of A and that one is P of B modulo n, and this is what we wanted to show. So the proof is over. Okay, now here is a thing. We are going to say that an integer a, for example, is, let me write it down, then you will understand. We say that an integer a is a solution of the congruence congruent to 0 mod n, where px is like that, is a polynomial with integral coefficients if P of A is congruent to 0 mod n. If P of A is congruent to 0 mod n. And now the above theorem has a small corollary. The corollary says this: if A is a solution of the congruence P of x congruent to 0 mod n, and A is congruent to B mod n, then B is also a solution. Okay. So let's see the proof. Since A is congruent to B mod n, it follows from the above theorem, that is theorem 4.4, that P of A is congruent to P of B mod n. However, it's also given that A is a solution of this, so P of A will be congruent to 0 mod n, and that is why P of B will also be congruent to 0 mod n. But P of A is congruent to 0. There is something wrong with this side of the board. So P of B is also congruent to 0 mod n, that is B is also a solution of our original congruence. Okay, so that is the proof of the corollary. And now we can finally go to this divisibility tests. The first one of which gives us a criterion for precisely when a positive integer is divisible by 9, and then we will see divisibility by 11. So the 9 one looks like this. Let n equal to, n is a positive integer and this is the decimal expansion of n, a m minus 1 10 to the power m minus 1, and it goes like that in this pattern, and eventually we have a1 times 10 plus a0. B, the decimal expansion of the positive integer n. So the digits of course are all between 0 and 9, including 0 and 9 of course. I mean, those possibilities are also there. So each ai is non-negative and less than 10. Either you write less than 10 or you write less than or equal to 9, same meaning. And that's not all. And S is the sum of the digits. Am. Then 9 divides the original integer n if and only if 9 divides this sum S. So let's now see the proof of this. So we are going to take the help of theorem 4.4. We recall theorem 4.4. It says that if we have a polynomial with integral coefficients, right, and we have two integers a and b which are congruent to each other modulo n, then the polynomial evaluated at a will be congruent to the polynomial evaluated at b mod n. In this case, that polynomial is this. In fact, this itself is not the polynomial, but the polynomial can be derived from this. Consider the polynomial function let me write here p of x equal to, so the coefficients will be these ai's and it will go from 0 to m. Whether you take I here or k here, it does not really matter. This is a dummy variable, so whatever name you give it, it's not going to change anything. With integral coefficients. And in place of A congruent to B mod n, what shall we take? Note that our modulus n should be 9, and conveniently we can consider the congruence 10 congruent to 1 modulo 9, which of course is true. Since 10 is congruent to 1 modulo 9, it follows from theorem 4.4 that P of 10 is congruent to P of 1 mod 9. But P of 10, if you go back to what capital N is and what P is, if you evaluate P at 10, you actually get nothing but N. And what we can write this directly because that's how N was written. However, what about P of 1? For this, you may write, you may directly write S here, but let me just write a little bit of how that is S. 1 to the power I. So this is nothing but the sum of all the coefficients ai of our polynomial function, and that in fact is nothing but S. Hence, N is congruent to S mod, I hope I have written 9 and not N here. So we know that two integers are congruent to each other if and only if they leave the same remainder when divided by 9. This is a result that we have already seen when we were discussing congruences in general. So that is why if 9 divides one of them, it also has to divide the other. Why? Because say 9 divides S, what does it mean in terms of remainders? It means that the remainder that S leaves when divided by 9 is 0. So that should also be the remainder when you divide N by 9, and that is why 9 will also have to divide N, and conversely. This implies that 9 divides N if and only if 9 divides S. So for this if and only if, you do not have to work for the two directions separately, you are getting everything at once. If and only if 9 divides S. This is in fact a divisibility test which we are taught in school itself, but at that time of course we are not exactly told the reason why this is true, but now we see why this is true. And if we are given a large integer, straight away trying to divide it by 9 and seeing whether you are getting 0 remainder, it's computationally it may be heavy. However, if you add the digits, then that number naturally becomes much smaller than the original number. And note one more thing, that say you have an extremely big number, you want to check if it's divisible by 9. So by this result, what you do, you add all the digits. You do not miss anything, okay? You add all the digits, that gives you another number. That is also somewhat large. not as large as the previous one, the original one, but still somewhat large. You can then add the digits of that new number and get another sum. So the original one is divisible by 9 if and only if this intermediate number is divisible by 9, if and only if the still smaller sum is divisible by 9. So by repeated application of this, you can actually reduce the work to a very small number. Okay, so it's not that you have to work with that s itself. Taking that s as your new number, you can then apply this once more, as many times as you want, until you get a fairly small number for which you can directly check whether it is divisible by 9 or not. Okay, so that's divisibility by 9. Next, there is one more divisibility, 11. That is by 11. So that is this next theorem. Do you notice one more thing? Everything has been possible because of this congruence and because of the fact that we are getting 1 here. And evaluating a polynomial at 1 gives us a very nice thing like that sum of digits, sum of the coefficients. In general, that's not the case. I mean, not with every number. It's because 10 is congruent to 1 mod 9. That's why we have things conveniently like this. There is one more thing that one can consider in place of this. Namely, 10 is congruent to minus 1 mod 11. Now, evaluating something at minus 1 may not be nearly as easy as evaluating it at 1, but still you will get something fairly simple, and that's what we are going to see next. So, the statement begins just like that one. Let n equal to same, the beginning is same. A1 times 10 plus A0 be the decimal expansion of the positive integer. N, and accordingly these coefficients or the digits are all satisfying these inequalities, and let this time we will consider not the sum of the digits but an alternating sum, this one, A0 minus A1 plus A2 minus A3. So if the suffix is odd, we have minus, if it's even, we have plus. So with the last one we have to write A minus 1 to the power n. So this is an alternating sum where we do have all the digits, but the signs alternate. I should perhaps write minus here. Signs alternate between plus and minus. Then 11 divides n if and only if 11 divides t. And you can almost immediately see why, given that you have seen the 9 case. But still, we have to write the rigorous proof. If and only if 11 divides t. The proof also begins just like the previous proof. Consider the polynomial. Polynomial is also exactly the same polynomial. Summation aix to the power I where I varies from 0 to n with integral coefficients. And straight away, since 10 is congruent to minus 1 mod 11, it follows from theorem 4 whatever we need. That P evaluated at 10 this time is congruent to P evaluated at minus 1 mod 11. Okay, and if you evaluate P at 10 like before, you are going to get n, capital N. But P of minus 1 is in fact that alternating sum T. And P of minus 1 is T. Hence, N is congruent to T mod 11. And that is why, like our same argument, N and T will leave the same remainder when divided by 11. And that's why if any one of them is divisible by 11, then so is the other. This implies that 11 divides n if and only if 11 divides t. Okay, so these are the two divisibility tests that we have in this text. Now an illustration finally of these things to a number, an actual concrete number. So this is example 4, 5. I don't exactly understand the numbering scheme of the things in this book, but I never tried to understand also. It's not that important. For example, in Tau's analysis, he doesn't number examples separately, theorems separately. He just straight away continuously numbers all the items. For example, you will see theorem 4.4, after that whatever appears, whether it's example or remark or anything else, that will be numbered 4.5. So that is his numbering scheme. But here's something else. So the number here is 1571724. Okay, so without writing much, let us just straight away calculate the sum of the digits s and the alternating sum t for this number n and see what they are. This number is fairly large, so if you go for direct division by say 9 or 11, that may take time. But now that we have our test, we can apply that here. So what will be s? S is going to be 1 plus 5 plus 7 plus 1 plus 7 plus 2 plus 4. So how much will it be? I think I messed up. Let me just try once more. No, something is not correct. 1 5. Did I take it down wrongly? 1571724. Okay. Oh, okay. Yes. Yeah, I was adding wrongly mentally. You know how bad I am at this, right? So this is 27. Since I was thinking of 4 here but adding only 2. Since 9 divides 27, we have 9 also dividing n. So it's that quick if you apply the test. Also, what about t? Calculating t is easier than calculating s because there are many cancellations. So alternating sum, we start from the units digit and then alternate between minus and plus. So this will be 4 minus 2 plus 7 minus 1 plus 7 minus 5 plus 1. So 2 plus 7, 9, 9 minus 1, 8, 15 minus 5 is 10, 10 plus 1, 11. Oh, so here the alternative sum is itself 11. Since 11 of course divides 11, so we have 11 also dividing n. So this number is simultaneously divisible by 9 and 11. It may be of course divisible by other primes, but we know at least this much. And that's where this section ends. The material ends, but after that we have exercises. That of course we will start solving next week. So that's just it for tonight. Tomorrow we have, what do we have? Functions of class 11. So see you with that tomorrow. Until then, this is me, Lucifer from A Mathematical Group. Have a nice day.